So the standard enthalpy of formation, or H naught sub F, is the change in enthalpy for the reaction that forms 1 mole of the compound from its elements with all the substances in standard state. So, if I have all the elements in the standard states, and that produces 1 mole of compounds in the standard state, then my enthalpy change is going to be equal to my standard enthalpy of formation. Okay, and as mentioned, right, our enthalpy, our standard enthalpy of formation values are usually going to be reported at 298. So these enthalpy or standard enthalpy of formation values that we're looking at are actually usually cataloged in a data table or an appendix in the back of your book. Okay, so on the next slide we'll look at the charts and compare some of these things. But for right now, what we need to understand is that if more than one form of an element exists under standard conditions, right, if you have multiple forms, then the most stable one is used. So the one that has the standard enthalpy of formation value equal to 0 is going to be most stable. Okay, and the stoichiometry for these types of reactions are always for a single mole. And because of this, your standard enthalpy of formation values are always given in kilojoules per mole. And we'll see that on the next slide when we actually look at the data table. So here's a standard enthalpy of formation table. I believe your collection is seen in the back of the book in Appendix C. But as you can see, you have delta H standard enthalpy formation values for various substances. And you can look at the stability values. So silver in its solid state, right? Its standard enthalpy value is 0. So we know that that's our standard state. Same thing with the aluminum. Okay, bromine. Okay, it's a liquid in its standard state. Okay, graphite here, you notice carbon in the graphite state is 0, so it's the standard state for that. Okay, so you can see what we mean by your standard enthalpies of formation values needing to be in the standard state. So you select the one that is most stable. Just like you see here with the graphite versus diamond option. Okay, so this is the type of table you may need to use in order to utilize this. So we'll proceed through and we'll come back and use these a little bit later. So first things first is we should be able to establish if a reaction represents a standard enthalpy of formation. Okay, so there's things we need to consider. We should only have 1 mole of product. Okay, elements used to make the product must be in the most stable form, as we talked about on the previous slide. Those enthalpy of formation values should be 0 for those that are in the most stable form, and you should only have a single product. So you may be able to kind of infer this on your own, but you may have to use Appendix C because you're not familiar with the compound. Okay, so if we look at this first equation, the first thing we look at is how many moles of product we have. Okay, in this situation, we have 1 mole. Okay, so our first necessity, or our first characterizing factor, is accepted and correct. Alright, elements used to make the product must be in the most stable form. Okay, sodium typically is a solid in normal conditions, and oxygen is a gas. Now, you may need to use the chart if you're not familiar with it for right now. You would be able to see that they are in the most stable form based on the data from Appendix C. But in this situation, we kind of have a good idea of what would be in standard state and wouldn't be in the standard state. Okay, so our elements used to form the product are in the standard state, okay, in its most stable form. And last but not least, we do have, in fact, a single product. Okay, so this example here, we know that our enthalpy change is going to be equal to our standard enthalpy of formation value. Okay, so we could definitely use this setup to calculate our delta H. The next equation, if we look at it, does not fit some of the categories or some of the necessary features for standard enthalpy of formation equation. So the first thing we look at is we have 1 mole of product. Well, immediately when you look at this reaction, you see that we have 2 moles of product. So immediately our first equation has a problem. Okay. Additionally, let's look at the product value, or sorry, the products, the reactants used to make the product. Okay, so elements used to make the product must be in the most stable form. Okay, so you could look this up obviously in table C, or excuse me, appendix C. And you'd notice that gaseous Cl2, that is the standard state, that's the most stable form. But if you look at potassium, which is a metal by the way, being in liquid state, is definitely not going to be the most stable form. Okay, so characteristic number 2 is a problem as well. The only thing that actually does fall into this category is the fact that we have a single product. Okay, so we can make some adjustments to this equation in order to make it work. But as it stands, the delta H is not equal to the standard enthalpy of formation. So we wouldn't be able to utilize this in the way that it's written now. Okay, but in order to adjust that, we could change our state of our potassium. Okay, make sure that it's in the solid state. We could divide our reaction by 2 and all of the coefficients, and subsequently we'll get 1 mole of a single product. So this would be an acceptable setup right here for our standard enthalpy of formation. So if we go ahead and we look at this final equation, we almost immediately notice that there's some major issues in terms of the standard state considerations that we've been discussing. Okay, so first of all, the way this equation is written, there is not 1 mole of product, there's actually multiple products, and it's definitely not a single mole. So requirement number 1 is not fulfilled, and requirement number 2 is not fulfilled. Okay, then we also need to look at the standard states, right? We could use appendix C, as I've been saying, or we could just kind of get an idea. In this case, we'd probably have to look at the state, or excuse me, at the appendix C in order to establish this one. But H2 is a gas at room temperature, O2 is a gas at room temperature. Okay, diamond, right? That's not the most stable form of carbon. Okay, and this sugar right here is definitely going to be in a solid state. So we have some of the characteristics that we need, although we still are going to need to fix one of our products. So what we do in this case, in this specific case, is we're going to have to flip the equation, right? And when we do that, we end up with a single product. Okay. We're also going to have to replace our diamond with graphite. Okay. And then we subsequently have a reaction in which your enthalpy value, your change in enthalpy value will be equal to your change in standard enthalpy of formation. So these are just a few examples to look at and to learn how to use appendix C alongside. So I suggest you go through and look at each of them. So we can use these enthalpy of formation values from the appendix C in the back of our books to solve for delta H of reaction values for various different reaction types. So we can use Hess's law along with the the values from the data table in appendix C to solve for delta H of the reaction. And we can do this if we know these enthalpy of formation values for all of the reactants and products. Okay, so if we have those available in the appendices, we'll be able to establish our delta H of reaction from these formation values. The second option is to use the equation below and the values from Appendix C. So we'll look at this option as well, but first we're going to look at how to do this in the context of Hess's law and Appendix C. So if we're given an equation in which we're being asked to find the heat of reaction, we can use the data table from Appendix C and those formation values and subsequently establish our reactants and our products various values within the context of the equation we're desired for which we want to solve. So from our table we can get our heat of formation values for our reactants. Okay, so we see that here. Our products. Okay, and we obviously have our various enthalpy values. Okay, so very much in the same way that we utilized Hess's law and did the manipulations of the equations by flipping them and multiplying them by specific coefficient values, we're going to be doing the same thing here. As you notice with this first equation, we have our formation value for C3H8. We actually have that as a reactant in the equation above. Okay, so we know for sure that we're going to need to flip this equation. Okay, so we reverse the equation as you see down here. And with that, we have subsequently also addressed the sign value associated with that equation. If we look at the next equation, right, we see that CO2 is our product, right? Notice that the coefficient in the equation we're wanting to solve for is 3. So in order to make the equation that we have here match, we're going to have to multiply through by 3. So just like we did when we did the Hess's law summations before, we're going to multiply everything through by 3. Okay, and that also includes the heat of formation value that we're going to be obtaining from our values above, or excuse me, our appendix. Okay, in this last equation, same kind of concept, right? H2O is one of our products. The coefficient here does not match what we need up here. So in order for that to match, we're going to have to multiply everything through by 4. Okay, and we've seen that. Alright, and we subsequently multiply our enthalpy of formation value by 4. So just like with Hess's law, and the reaction or the examples that we did earlier, we're going to sum all of our reactants, sum all of our products, okay, and we're going to cancel out the things that repeat on both sides, okay, and we're going to end up with an overall equation for what we desire. So now the question is, well, how do we figure out the heat of reaction? Well, what you need to understand is that your delta H of reaction is going to be equal to the sum of the individual enthalpy of formation values associated with each of the reactions that you utilized above. Okay, so your delta H of reaction in this case is going to look something like this. Okay, so you have the C3H8, we flipped that, so we have a negative in front. For the CO2, we had to multiply everything through by 3, so you see that here. Okay, and we had to multiply the H2O formula by 4, so you subsequently see that value there. So then we're going to go back to the numbers that we get from our enthalpy of formation table, okay, in the back of the Appendix C, and we're going to plug these numbers into the corresponding brackets here. Okay, we're going to carry out basic math, so it's going to be negative times a negative 103.85 plus 3 times negative 393.5 plus 4 times negative 285.83. Okay, and that should give us this value here. So this is how we utilize Hess's law and the enthalpy of formation values from the appendix in order to calculate our delta H of reaction. So this is a pretty involved process and can be somewhat time-consuming, but you are familiar with the Hess's law approach, and this gives you a good understanding of how to utilize the enthalpy values from Appendix C. So another way that we can solve for our delta H of reaction is by using this equation here. Okay, so we can take the sum of our products minus and subtract them from the sum of our reactants. Okay, we get our formation values from Appendix C once again, and basically just chug and plug numbers. We will need to take into account the coefficient values that we get from the equation. So notice CO2, right? We're going to have to put a 3 in front of that. Okay, there's a 4 in front of H2O. There's nothing in front of the C3H8. Okay, and we have a 5 in front of the H2O. Okay, so we do have to consider the molar quantities of each of these in the overall reaction. Okay, so notice I've taken the sum of my CO2 value plus my H2O, so my products, multiplied by their coefficients in the balanced equation, okay, and subtracted them from my reactants multiplied by the coefficients in front of them, their symbols in the balanced equation. So I'm going to get these enthalpy of formation values from Appendix C, just like we did in the previous example, and we're going to plug those numbers in. Okay, you plug them in, right, do the math, and you subsequently get your delta H of reaction value. So this is actually really straightforward. Notice that for O2, our formation value is 0, right? It's in its standard state, so that makes sense. Make sure that you're paying attention to which oxygen to select. You know which one to select based on the state of the matter. So in this case, we get a pretty straightforward approach to solving a problem. So it's a lot less complicated than the previous example that you were shown. Okay, so other problems that you may be asked to solve for is to actually figure out a missing value besides delta H of reaction. So I might know what my delta H of reaction is, and I might be missing one of my enthalpy of formation values. So this will be a type of a question that you'll find on the AP exam as well as our upcoming exam. So in this situation, we just set everything up exactly the same, but we definitely leave the variable that we're solving for blank. You carry out your basic mathematical operations just like you would after you've plugged in your enthalpy values that you know, and basically solve for your desired variable. So this is a very, very useful equation. It makes light work of more heavy calculations, more time-consuming calculations, but you should be able to do both for the exam.